Record on. Oh, let's hope it works out right. Okay, so this was the theorem, yeah. So if V is a vector space, finite dimensional vector space, and phi is a linear operator on V, then we defined this generalized eigenspaces. Yeah, V lambda is basically on this set of vectors V in V, which is annihilated by phi minus lambda I power n for some n. Yeah. So this is an invariant subspace, and and the theorem says that if the characteristic polynomial of phi is product of linear factors, then we can decompose phi as dx sum of v lambda 1 to v lambda r, where lambda 1 to lambda r are distinct roots of the characteristic polynomial. Yeah. So let's see. I don't know why this is in the middle of the screen. Okay. Okay. So I forgot. Yeah. So we showed that V lambda is a invariant subspace. So I suppose there was no doubt about this thing. So V lambda is an invariant subspace, and we saw that the characteristic polynomial. So if you factor the characteristic polynomial like this, then and then you define this GIT as this guy, yeah, and FIT as T minus lambda I power MI. Okay. Then we see that the FIT and GIT are co-prime polynomials, right? And then I said because of some division algorithm kind of arguments, you can show that there exists polynomial A and B such that AFI plus BGI is 1. Yeah. In fact, so this is one way of, so one can simplify the proof a little bit if you prove a slightly stronger version of this result. Yeah. Which I'll, okay, so maybe I'll mention it here. So see, if you consider these GITs, yeah, as I vary between 1 and R, then GIT, so there's no common factor for all the GIs, right? So, I mean, for instance, T minus lambda I is not a root of GIT. So, I mean, GIT doesn't have any. So there is no none of the factors of the characteristic polynomial divides GIT for all I, right? Does that make sense? Yeah. So if you think about the collections G1 T plus G2 T GRT, then collectively they are co-prime, meaning there is no common factor for all the GIs. And in such a case, again, you can find polynomials in FT such that so maybe I'll write it here, but and then it will that process will give you things at one go. Yeah. So let me see. So somehow it's not allowing me to write. Okay, let me just restart this again. Yeah. Okay, so you also have a relation between GITs. So yeah, what is going? So summation. I can't write again. This is becoming a bit irritating. One second, let me try this at some. Okay, it's not working. Okay, let me, since I have to write a very little, let me write it using my hand and see if it works. Yeah, so there is a relation among GIs, which is summation CI times GI I equals 1 to R is also 1. Okay. So because GIs have no common factor, so this again follows from the fact that FT is a Euclidean domain in some sense. So division algorithm works. So you do it two at a time. So basically what it says is that if the GCD of two polynomial is some R, then is F and G is some H, then you can find A and B such that their linear combination is H. That is the most general theorem for. So that is the result for Euclidean domain, which you can get from division algorithm. So if the GCD is some H, then you can write it as linear. So if you apply that successively for all this, then you can say that you can find these CIs such that, so you apply this inductively, then you'll get this as well. So what you get is that then you can take PI to be CI times GI of phi. Okay. And then what you'll get is PIs are, each PIs are projection, and their sum is actually 1, is the identity matrix. Yeah, so P1 plus P2 plus, and then the decomposition comes out more easily. Yeah, but so then the things comes out. Oh, it's writing now. Good. Comes out more naturally. But anyway, we even this method will work. meaning if you just assume this fact. So we saw that this decomposition works, meaning you look at the pi, and then pi is a projection on v lambda I, right? So last time we saw that it is indeed a projection. So we saw that pi is same as pi square. Yeah. So I don't know why it says 0 here. 0 plus pi square is what it should say. Yeah. So the first term is 0, the second term is pi square. Yeah, and then we saw that the image is exactly v lambda I. Yeah. So I mean, so I've left this as a homework, phi minus lambda I power mi. So today maybe I'll give an argument for why this is true. So in terms of minimal polynomial, and then I'll leave it as a homework that the characteristic polynomial of v lambda is precisely phi minus lambda is precisely fi phi. Okay, so you'll have that I'll leave as a homework for you guys. Okay, and then we saw that the image is precisely, the image of pi is precisely v lambda I, and so whenever you have a projection, so here then I started defining this QIs. Yeah, so whenever you have a projection pi, identity minus pi is also a projection. So this is the standard. I mean, there is no trick. This is something standard. So if you haven't seen it, then it looks like a trickery. But it's like E is an idempotent, then 1 minus E is again an idempotent. So it's basically that kind of principle. So Qi is again a projection onto the other factor, Wi. Yeah. So see, V is going to be v lambda I plus wi. So this we have already seen. For projections, we saw this property, right? If you have a projection, then the vector space is same as v lambda I plus the kernel. Yeah, is same as the image plus the kernel. So this doesn't happen for any linear operator, but for projection operators, we know that the vector space is same, because basically kernel and the image doesn't have any intersection. So, but anyway, we saw that in the beginning. Okay, so now, so we have split out this Wi, and Wi has smaller dimension than V. Yeah. So so this was I think this was the argument. I says your meeting will end in 10 minutes, but I thought I had an account. Okay, so once the meeting ends, we will restart. Yeah, this I guess today's video is going to be a mess. Yeah, so hopefully in 10 minutes we'll figure out this part at least. So so this decomposition, I hope the fact that Qi is a projection and image Qi is Wi is clear. Yeah, from last time. I think his question was how Anarga's question was how we are going to use induction. Okay, so we look at so W is a phi invariant subspace, because W is basically image Qi, and Qi is how was Qi defined? Qi was A fi phi. Yeah. So for these kind of, when it's a polynomial in phi, then it is phi invariant is clear. Yeah. So Wi is a phi invariant subspace, and what you do is now look at phi restricted to W. It's a smaller subspace, and it has a characteristic polynomial, which so, and remember, this was also a homework problem, that if Wi is a subspace of V, then the characteristic polynomial of phi restricted to Wi is divides the characteristic polynomial. Yeah, so it's again the sum of linear maps, right? So so characteristic polynomial of phi prime is again is actually G1T. That also you can see, but that also we argued. But at least is product of linear factors, right? So in fact, we know that this decomposition gives you A and C, and so I gave an argument for it why it is why it is G1T, but at least it's product of linear factors. So so by induction hypothesis, we can write. So this is where we use induction. Yeah. So now you use induction on with W prime and phi prime. Yeah. Phi prime is an endomorphism of W1 and phi prime. So phi prime is a operator on W1, and dimension of W1 is less than dimension V. Yeah. The characteristic polynomial is product of linear factors. So you can write it W1 as the sum of W lambda 2, W lambda R, where W lambda 2 is lambda 2 eigensubspace of W1, generalized lambda 2 eigenspace subspace of W1. W lambda R is generalized lambda R eigensubspace of W1. Yeah. So this line, this first line is clearly from the induction hypothesis. Is that clear, Anarga, so far? Yes, sir. Yeah. So now but we want to say that V is V lambda 1 plus V lambda 2 plus V lambda 3 and so on. So we'll have to show that W lambda 2 is same as V lambda 2. Yeah. And W lambda 3 is same as V lambda 3. So that means generalized lambda 2 eigensubspace of W1, which remember is a subspace of V. Yeah. Is same as W2 is same as lambda 2 eigensubspace of V, generalized eigensubspace of V, and so on. Yeah. So though I wrote it as homework, but since you asked, so I'll explain you why this is true. So of course, if you take an element of W lambda 2, it's a lambda 2 non-zero element of W lambda 2, then it's a lambda 2 generalized eigenvector in W1. Yeah, and W1 is a subspace of V, so that element is already contained in V lambda 2 as well. Yeah. So since W1 is contained in V, we have W lambda 2 is contained in V lambda 2. Yeah. And in fact, V lambda I for each I. So we'll just prove it for lambda 2 and the rest of the proofs are similar. Is this okay? This containment? So if you take a generalized lambda 2 eigenvector in W2, then it's of course a generalized lambda 2 eigenvector of V as well. Yeah. And hence it is contained in V lambda 2. Yeah. So we only have to prove the other inclusion. So this inclusion is straightforward because of the definition. So now you take some generalized eigenvector in V lambda 2. Yeah. So let's call it V. So it is in V lambda 2, which is contained in V. Yeah. Now, of course, any V is this capital V is basically V lambda 1 plus W1. Yeah. So we can write it uniquely as some element V1 in V and some element W in W1. Right. We saw this here, right? The first claim in this page was V is V lambda I plus Wi. So you put I equals 1 here. You know? So where did it go? Yeah. So we can write V as V1 plus W for some V1 in V lambda 1 and some W in W1. And in fact, it's unique because it's a direct sum. Right? So what will the first projection do? first projection will send, so this is how projection operator works, yeah? It will send the first V1 to, it will send V to V1 and Q1 will send V to W. Yeah, this is how, because P1 plus Q1 is identity. Yeah. So what we get is that P1 V is V1 and Q1 V is W. Yeah. So all I have to show is that V belongs to W lambda 2. Yeah. So that is same as saying that yeah, V1 is 0. So if I prove V1 is 0, then W is same as V and we are done. Yeah, so that is what we are trying to do. So, sorry. So now you, what does it mean to say P1 V is V1? P1 was B G1 phi applied to V. Yeah. So this says that B G1 phi of V evaluated at V is V1. Yeah. But but V is in V lambda 2. Yeah. And V lambda 2 is precisely, I have written it here in the next line. Yeah, so maybe I can put this in the same line. V lambda 2, this is same as V lambda 2. Yeah. So since image of P2 is V